Okay, good morning everybody. Thank you for the introduction and for inviting me in this beautiful place and interesting conference. What I'd like to do in my talk this morning, as you can see from the title, is to focus the attention on the generation of high-resolution land cover maps in general, taking into account the main challenges that currently we have in remote sensing for the generation of this data, especially when we work at very, or let's say, high resolution in terms of geometrical conditions. Well, the outline of my presentation will follow this path. I start just introducing some common elements that are, I think, well known but important to understand the scenario in which we are working. Then I'll focus my attention on one very important point, which is connected with the availability of labeled data for defining the models that generate these high-resolution land cover maps. I'll briefly mention about foundation model. I don't enter in any mathematical detail, of course, in this presentation, but just to give you the flavor of what is now the frontier of the activities in the generation of this kind of products. And then I would like, in the last part of my presentation, to show you what we are doing in terms of generation of high-line cover maps, high-resolution line cover maps, in the framework of the Climate Change Initiative of European Space Agency. Well, let's start with some introductory concept. I think that everyone is aware of the huge amount of data that currently we have from satellite, constellation of satellite, aircraft, now also drones, data that are characterized by different properties. We have many systems that acquire passive data, we have multispectral data, we have hyperspectral data, we have images with very high geometrical resolution but limited spectral resolution, and we are in a condition in which we have, of course, data acquired by active sensor, synthetic aperture radar, polarimetric data. We are in the condition in which we start to have a growing number of LiDAR data, also data that characterize what happened in the subsurface of our planet, which means that we have a huge number of different physical measurements that help us to characterize the land cover. Of course, different measurements capture different properties of the land cover and can be used sometimes in a synergistic way to have a detailed mapping. But from the perspective of the data, another important part is connected with the resolution with which we can acquire the data. We have data that have high spatial resolution, we have hyperspectral data with high spectral resolution. But then when we talk about land cover mapping, it becomes very important the temporal resolution, the revisit time, in order to be able to capture what is the signature, what is the temporal signature that we get for the land cover during, for example, a full year, and to get this dynamic in order to represent what we have on the ground. Now, the data are one part of the story. Of course, when we talk about generating high-resolution land cover map, the other part are the map themselves that can be generated with many different properties and characteristics. We are in the condition now in which we can generate map at a very large scale using the sensor and the satellite that we have. Of course, when I refer to the map, I refer to different kinds of products, depending on the legend and the classes that you like to recognize. We can have a very general representation of what we have in terms of land cover, or we can have a much more detailed representation when we focus on specific applications. For example, agriculture, where the target is not to recognize just general classes, but to recognize the single crops. We are working in a project in which we are trying to recognize 80 different crops in a scale which is subcontinental scale. Of course, depending on how you define the problem, you are in the condition in which you need to identify the right data to use, the right sensor, and of course the right geometrical resolution that represent what you are doing. If I move from agriculture to forestry, I can say the same. Of course, I change completely the kind of legend of the map that I have to generate. I have to represent the species that we have that characterize the different trees, and so on and so forth. What is important is that depending on the classes, the legend that you have to define, then it becomes important to select the proper sensor for generating your land cover map. And if you need to have a very detailed representation in terms of semantics, sometimes you have to integrate different kind of sensor for the generation of the map, which increase the complexity of the processing. If you have to work at a large scale or global scale, this becomes still a challenge because it's difficult to get proper processed data for that kind of purpose. And there are other challenges. I'll show you later what you are doing in the climate, but in some cases you have to generate a land cover map at high resolution by going back in time, which means that you have less data available, you have less label data for training the classifier, and this represents for sure a quite important challenge. Well, if you look at what is done in these years, you can find in the literature and available now products that are high-resolution land cover maps that reach the global coverage. We have, in this table, you can see some example of this kind of products. There are others. But we are in a condition in which we can get the representation at 10 meters, 30 meters. This is what I mean in this talk as high resolution of what is happening at the land cover in different parts of the world. We are in a condition in which different products are characterized by different classes, different legend, and also different properties, even if the resolution are similar. I'll show some example later on in my presentation of what I mean. But there are products that are generated starting from optical data, others that are generated starting from SAR data. In some cases, we have the merge of the two sources of data. There are many of these kind of land cover maps that are now provided, and we will see much more in the near future. Well, there is then the third component of this reasoning. We have the data, we have the map, and of course, for generating the map, we have the automatic analysis that we have to implement on the data. If we work, of course, at global scale or continental scale or also country scale, the only way is to use automatic approaches now for generating this kind of products. And when you look at this, there are many challenges still to be addressed. When you try to generate products at large scale, as many of you know, we have the problem of the pre-processing of the data, harmonization of the quality of the data in different areas, especially if you have to use time series for representing the dynamical land covers. This is a big challenge. As well as another big challenge is connected with the label data that we use for the training of the models that generate the map. We can, of course, use classification techniques, but the accuracy that we get, the quality of the map strongly depends on the label data that you use. And the label data are associated with uncertainty, especially when you try to generate a large data set, as we are trying to do now for supporting the power of AI for the generation of this kind of maps. There are then other important issues related to the harmonization, the consistency, especially if you generate time series of land cover maps. And this is something that should be injected in the data analysis process, as well as we have to focus on post-processing. Well, just to enter a little bit more in detail, in the next part of this talk, I'd like to stop and discuss a little bit about this relation, about the label data that we have and the definition of classification models that should take into account the uncertainty that we have in the label data for the training, but also then in the products that are generated. And in particular, I would like to address this, focusing my attention on the label data and relating what is happening in terms of classification techniques when we look at the label data that we have. I think it's useful to take a look to the evolution that we had in the development of classification models And in this diagram, what you can see is the number of label samples that were typically used for the training of the classifier versus the evolution of the classification techniques. We started in the 80s with the first system for producing length over maps with the first data available by using classifiers that were mainly statistical classifiers based on Bayesian theory. We used simple methods with limited requirements on the number of label data for the training. That is, okay, few hundred samples for performing the training of a classifier. And also because at that time, the purpose was to generate length over map on very small areas. We did not have the capability, of course, to work at large scale. Then, jumping to the early 90s, we started to see the use of artificial intelligence. This was not called artificial intelligence. We talk about neural networks with a simple model, multi-layer perceptron, radial basis function neural networks. Models that, however, had an architecture that was more complex than the typical architecture connected with statistical classifier. More parameters to estimate, and so an increased requirement on the number of labeled samples. This is something that evolved in time. I think another important point in the remote sensing community was the introduction of support vector machine and kernel methods. We worked on that at that time. We were in 2004, where the machine learning became more popular, and also the development of methods based on sparse solution, on the capability to represent the classification problem using the maximum margin criterion, made the machine learning techniques more robust to the number of training samples. But of course, at that time, it was possible to generate already larger training set with a larger number of label samples. Another point that I'd like to mention that I think is quite relevant is what happened in the surrounding of 2010, where a more intense activity was devoted to the use of semi-supervised methods. That is, I can increase the number of samples for the training, but some of the samples don't have any label. They just are used for capturing the structure of the classification problem. So it becomes much easier, of course, in this context, to generate a large training set. But of course, with samples that in some cases are labeled, in some cases are not labeled. The cost of the unlabeled samples is nothing, just the processing of the data. But then if I go ahead, the other big jump that we had was in 2015, when starting from the activity that had been developed in computer vision, we imported in remote sensing the use of deep learning. Deep learning changed completely the landscape because we have models that are characterized by millions of parameters, which means that the requirement on the training samples is completely different. If I have to estimate millions of parameters, I need millions of labeled data for a proper estimation. And this is, of course, a big challenge for our community, because we are not in computer vision. We are not to label images with cat table. We have to be in the condition in which we label samples that, as you know, are much more complex to represent. And the last frontier, what is now the subject of a lot of activity, are the foundation models. That change also the perspective. I'll comment later on the way in which you perform the training. But in foundation model, we have the models that are characterized also by 1 billion of parameters, which means a completely different scenario with respect to the past. Now, on the basis of this, we had this evolution in the requirements of the number of training samples. Starting with deep learning in 2015, we started to see people working to the generation of large annotated training samples for remote sensing. There are, if you look at the literature, now many data set benchmarks that have been generated with 1 million of label samples or hundreds, thousands of label samples. These are different for the different application domain. We have benchmark focus on different application, benchmark focus on the use of different sensor, different resolution, different coverage. So a lot of information that is provided in this benchmark that are available to the community, that try to support the learning of deep architecture. But one key point is connected with the quality of this benchmark. Of course, what you represent in the label data is crucial at the end for the success of the classification. And here we have a lot of problems, I think, because in the most of the cases, this benchmark data set are not associated with measurements of uncertainty, measurement of quality. You have a lot of label samples, but we don't know if these label samples are properly representing the reality. Well, I'd like to work a little bit along this line, elaborating what are the main sources that are typically exploited for generating this label data set. Of course, one possibility is to start with the standard approach. We use ground collection of label data. This is very typical for our community. But as you know, we cannot generate millions of annotated samples. We can have few highly reliable label samples. Another way is to work with photo interpretation. Photo interpretation helps to increase the number of label samples because we are in a condition in which you can perform this operation without going on the ground. But this is challenging. I mean, we are in the condition in which we need experts to perform photo interpretation. Only in a few cases you can try to have some crowdsourcing, but this is not the case of computer vision, where everyone can put a label on an image in a qualitative way. There are then other activities that try to exploit what is done in terms of infrastructure with sensor networks or other kind of opportunity sensor that can be exploited for integrating annotated label for the training set. But this is not really very extended. One of the most typical trends now that we see is related to the use of digital map, obsolete digital map, for trying to annotate the samples that you like to use for the training of your models. This is something that is widely done, and is done by considering sometimes map that represent the label of a pixel. Sometimes you work with a vector map, where we don't have the single pixel modeled, but you have a polygon representation of the land cover. I'd like to discuss a little bit more in detail this, because all these data sources that we have are associated with intrinsic uncertainty. The uncertainty is propagated then in the model and then in the products, which means that when I look at the different possible data sources and to the uncertainty, we have uncertainty connected with the accuracy of the input data. For example, if you use all digital map. We have uncertainty which is related to the temporal discrepancy. I mean, I take the data that refer to a different time, so I may have changes. We have uncertainty which is related to the way in which the information in terms of resolution is reported in the maps. And we have also uncertainty, very important, connected with the semantic of the representation of the land cover classes. I'd like just to spend a few words on this part, all this source of uncertainty, because I think this is extremely important at the end. When I say that we have inaccuracy, I am in a condition in which I say that if I use an old map for trying to have a weak label for representing my new samples, of course, what I'm doing is to propagate the error of the old map in the annotated samples. This should be taken into account, because this is a limitation in terms of the information that I provide to my machine learning techniques. When I say temporal discrepancy, we are in a condition in which what it may happen is that I take map that represent something that is changed on the ground. In the most of the cases, maybe you have reliable labels, but in some cases, of course, you have the changes. And you need to take into account that. When I say ambiguity in the representation of the information in the maps, I refer to the fact that in many cases people take a low resolution map and try to aggregate the label to higher resolution images. Or they take a vector map and do the same. But this, of course, can create a lot of uncertainty if you don't model properly this in the process. For example, if I start from the representation at vector level of land cover classes, I am in a condition in which typically what you do is to use a minimum aggregation unit, which means that I have a label for my polygon, but then if I look at the detail of the images, what happens is that this label in reality is associated with two different semantic classes. And maybe I have more natural classes in my data, in my image. And so if I try to associate pixel-based, the label of the polygon to the pixel of the image, of course, I'm doing in the direction that create confusion. Because if I like to do this, I need to properly manipulate this source of data, decompose, trying to get, looking at the feature space, what is happening in terms of semantic classes, and then performing the association. Other example, the semantic inconsistency of the legend. Every product, as you know, has associated a legend that can be very general, also very detailed. But the key point is that when I say crops, I'm saying something which is very generic and can be translated then in different way in different maps. Okay, if I say I represent the crops, yes, but what kind of crops? Okay, in different areas you may have different categories, different kind of crops that are represented. They are not all the same semantic. And so the temporal signature, the spectral signature change with respect to the kind of product that you use. And this can be iterated. Okay, if I see tree plantation, okay, but what kind of tree plantation? And if I just take these generic labels and I don't look to the definition, what happens is that I may annotate my samples in a way that is not consistent with what I'd like to do. Okay, I take the example of the crops, but also for broadleaf conifers, what is the definition? Because if I work at 30-meter resolution, I have always mixed representation of the classes. So typically, there is a quantitative definition of this class that represents a threshold for putting a label that may be different in different products. If we take everything together and we generate 1 million data set samples, then maybe that we are taking together different things that create problems then to the classification model. So the key point here is that we are in a condition in which for generating this very large data set, you have two possible strategies. I take different information sources, I characterize the uncertainty, and I comment in 1 minute on that. And then I try just to take the samples that are more certain for the generation of the large training set. Or I can use all the sources that I have, but I have to associate to these information sources the uncertainty, so that also the classification system is aware of the uncertainty associated with the samples and can model this in the training. Of course, this with the objective to generate products that are accurate, and also with the objective to generate products that can be associated with the uncertainty information, because a map is not sufficient in many applications. I would like to understand what is the reliability of each decision of the classifier. Now, when I say modeling uncertainty, of course, I go in a domain in which we need to understand the source of the data, and we need to understand how, from then a technical, mathematical, scientific viewpoint, I can characterize the uncertainty. I don't enter in the detail, but when we work with the problem connected with the intrinsic error that we have in the maps, we can try to model this as a noise in the classification system, taking into account that we may have class-dependent noise with systematic error in some classes, in some maps. Or we can try to model with different strategies that represent the complexity of the problem and the potential error that you have in the map. If I say that I work with on temporal discrepancy, of course, I have to model the uncertainty with a kind of probability of change. So there are classes that I don't expect are changed. There are classes that I expect are changed. There are ways for representing this, also looking at what is happening in the feature space when you process your data and putting the possibility to model the uncertainty in this training procedure. When I look at the problem when we associate low resolution map with high resolution data, or when we associate vector map and the label of vector map to pixel in new training set, what we have to do is to apply a kind of analysis that drive a decomposition of this information. Now, I don't have time to enter in detail. We have worked a lot in the past on this. We are still working on that, in order to include in the automatic training the capability to distillate from these products data that represent properly what is the land cover. And we did some tests in the past in order to see what you can do. We started, for example, with Corinne land cover for Italy, and then we distilled from the vector map the information on some of the main classes and trained the machine learning classifier to generate new map, in this case at the scale of Sentinel-2, 10-meter resolution. That is representing what is the input data, which is associated with polygon, of course, with vector maps, representing properly the information which is inside, and then obtaining classification at 10-meter resolution. If you take the label as they are, you have a huge amount of error. If you can try to understand, working on the data, of course, on the feature space, what is the actual composition, you can get significantly accurate results. So, I'm saying that we are in the condition in which we have different sources of label data, and different sources are associated with different kind of uncertainty. We need to model the uncertainty when we construct this huge benchmark data set. And we need to model the uncertainty so that we can generate large label data sets that are more representative of the actual information that you have on the annotation. By the way, then you can try to use data augmentation for increasing the sampling of your space and the representation of the samples. You can also use now generative models for creating additional samples. There are a lot of activity that you can do using active learning on difficult samples in order to increase the size of this data set. And you can couple this with the use of unsupervised approaches, like contrastive learning, self-supervised approaches that can complement the training. So what I'm saying is that we are in a condition in which the definition of this big data set should be coupled with the additional capability to model the uncertainty. Otherwise, we put significant limitation on the performance that we get. By the way, there are then different strategies that you can use in the learning of your machine learning model in order to take into account the uncertainty. I don't have time to enter in detail, but you can define, if you are familiar with deep learning architecture, specific loss function that include the uncertainty, also pixel by pixel, pattern by pattern in the learning. You can try to use different approaches to model the noise of this uncertainty. Or you can try to include in the architecture that you use weak supervision that is based on strategies that perform the training in your architecture, in your deep neural network, by taking into account the presence of the uncertainty. So, let's say, in summary, we start from our large data set characterized by the uncertainty. We define proper strategy of weak supervision, and then we are in the condition in which we can generate our products. Of course, in this talk, I'm referring to high resolution land cover products, also because this kind of approach is typically connected with the generation of high-resolution land cover maps. You don't use deep learning or better. This is not the typical case of using deep learning AI for producing land cover map at low resolution or medium resolution. Okay, just a few words about foundation models, since they are now the frontier of the research activity that is done. As you probably know, I was mentioning before, these are models that try to represent the semantic that is in the data by modeling the information in a feature space that is as more general as possible. In terms, the idea is behind this is I have models that can perform, for example, the classification zero shot, that is without any training samples. They capture the complexity of the problems. If you look at the literature, we have now, I counted 150 foundation models in remote sensing, okay? Many of them are, in my opinion, are not reliable at all. These are just a few examples that I took just to recall what is happening. But we have foundation models that are focused on optical data, foundation models that are focused on SAR, foundation models that work now also on hyperspectral images, on multi-sensor data. In some cases, they can represent time series in the processing. In other cases, they are based on just single instances. But the key point is that we have a growing number of this kind of approaches. And again, we have a problem of quality of what is proposed. Now, if I look a little bit more in detail, we have a condition in which these are 3 examples just of models that I took, but there are many others, okay? But when you look at the number of parameters that represent these models, the story is much more complex than in typical deep learning architecture, because we arrive at 1 billion of parameters for describing what is the semantic that you have in your data. And in order to use this kind of models, what is done is to use, in some cases, still labeled data, but in the most of the cases, you base a lot of your training on the unsupervised approaches, the self-supervised. You can use different kind of paradigm, okay? You can use contrastive learning, but the most widely used approach is to use masked image modeling. That is, I take my images, I mask a part, and then I try to reconstruct the part, so that I don't need external information for trying to get the process that is associated with the representation of the semantic in the images. Of course, this is something which is promising. We have, I told you, now many different proposed foundation models, and as I mentioned before, you have foundation models that are focused on specific data. In some cases, they are also focused on specific test cases. There are models that are suitable for specific kind of length covers. But this is still a domain where we need to work a lot in order to get something that is reliable at the end in terms of products. Okay? And when we look at the condition in which we are, I think the most important gap that currently is still present is that we are using approaches that are approaches of computer vision. Computer vision, by definition, is qualitative. I like to represent the label of my objects. In remote sensing, we are in a discipline, which is physics, which is quantitative. And we have the capability to model with physics a lot of, let's say, events, a lot of conditions. And this physics-informed information should be injected in deep learning architecture, in foundation models. We start to see this in terms of research, but we are still at the beginning of what should be done, in my opinion. Then when you look at what people are doing now, we are in a condition in which we use a large language model for coupling textual representation of the scene with the length covers. Okay? Very ambitious and potentially very interesting in terms of the results that can be obtained. There are other activities that try to distill the core semantic of foundation model independently on the sensor that is used. We have to be careful because different sensors get different physical measurements, and this kind of tentative should be done taking into account what is the nature of our data. And we are in the condition in which I think we need to work more as a community. Okay? We have 100 of foundation model, but what is the meaning of this? I mean, for having a proper training of a foundation model with 1 billion parameters, you have infrastructure of computation that are huge. And of course, this is something that can be done by big players in a proper way. Okay? One research group that generates his own foundation model typically produce something that has limitations. We should try to understand how moving from this spread activity to something that really results in reliable foundation model that you can use, take into account that there is physics in remote sensing. That's a key point. Well, let me go to the last part of my presentation. I'd like now to show you how these concepts are projected in an activity that we are developing with the European Space Agency. This is connected with the Climate Change Initiative of ESA, which is a flagship program that ESA started more than 15 years ago, and that tried to use remote sensing to generate products that support climate science. What we are doing here is to work on a project that is focused on the generation of high-resolution length cover maps. Now, if I look at the ESA program, what is done is to try to use all the data that we have available from the satellite in the archives to generate products that are associated with the so-called essential climate variable. I can try to represent at global level with global data set what is happening in different domains, from the ice sheet to the representation of what is happening with the variable on the ocean, the representation of what we have in terms of soil moisture, the presence of the fire. Emilio, who is here, is coordinating the project connected with the mapping of the fires. And of course, we have land cover. Land cover is important for climate change. On the one hand, we expect that changes in land cover can generate impact on the climate. On the other hand, I expect that changes in the climate can generate impact on the land cover. Now, in the first phase of this program, the focus was to generate a land cover map at medium resolution, 300 meters resolution globally. What we are doing in the activity that we are coordinating, here you can see the different partners that we have in the team. We have also a partner from Spain, which is the Research Center CREAF, who is working with us. What we are trying to do is to increase the resolution in order to see what is the role of the geometrical resolution in the land cover mapping in climate science. The idea is that on the one hand, if we increase the resolution, we can try to have a better representation of what is happening at a regional level. And of course, this is connected with possible action on mitigation and adaptation. But on the other hand, we'd like to understand if changing the resolution, we can get information which is different from the information that we get with medium resolution images. I'll then show what I mean in terms of representation of the results. So, of course, there are challenges, and the challenges are connected with what I discussed up to now. Okay, we are working in a domain in which we have to represent, of course, class legends that are relevant for climate science, which means that we have to also represent the seasonality of the land cover. And we have to use time series for performing our classification in each single year. Then this means that we have to use multi-sensor data. And one of the key issues is that we have to go back in time. So we have to use different data for generating time series of land cover maps. And this is challenging, as well as it's challenging to work in different climatic regions in the world, because the same kind of class has different spectral signature, different temporal signature, depending on where you are. So, of course, if you like to get products that are precise, this is very challenging. Also because the idea is that we go at a scale which is regional, subcontinental, and maybe in the future global scale. Which means that there are a lot of issues that you have to manage, including the consistency and the coherence of the products. Now, what we are doing here is to generate three kinds of products on the basis of the input we received from the climate community. We work to generate land cover maps at 10-meter resolution, that represent just a static photography of the area that you are analyzing. In our project, in the first phase, we produced a map for 2019 in the areas. And then in these areas, we generated a time series of land cover map starting from 1990. This at the regional level, so that we have the framework that provides constraints to the climatic model at subcontinental level. This is static, but then we have the time series. And we also have the capability to generate the information on the change on a yearly basis. Which means that every 5 years we have land cover maps, but we can localize where the changes occur on a yearly basis. In the first phase of the project that was completed a couple of years ago, we have worked to the definition of the pipeline for generating these products, and we have worked on three important areas for climate. One is Amazonia, where, of course, as you know, we have deforestation, conversion from forest to crops. And in Amazonia, we generated our static map for 2019 in the square, that is with the edge in green. And then we represented the regional evolution in the square that is in orange. In Africa, we focus on Africa Sahel, where we have extreme event, drought and floods connected with the climate change. And then we focus on Siberia, which is challenging from the viewpoint of data processing. There are few data and a lot of clouds in the optical data, as you may imagine. But it's extremely important because there, given the latitude, we see the effect of the climate change in an accelerated way in terms of land cover transition. The classes of the product that we generate are 16. You can see this is the legend. We have different classes that are representing the seasonality of the vegetation, which means, as I was mentioning before, we have to capture the information in time series, not in single representation with single images for each year. Well, this is the processing chain that we have generated. Of course, I don't enter in detail. The main point is that we have two branches, one for optical data, one for SAR. But the branch for optical data should be able to process data since Landsat 4 to Sentinel-2, so many different sensors, even if a passive sensor. And on the SAR, we process data from ERS 1 and 2 to Sentinel-1, again, quite challenging. Of course, there is a big pre-processing work that is extremely important in terms of harmonization of what you have in terms of data. If I go back in time, I start to have lack of data. And so it's complex to have something that is properly representative of what you are doing in terms of recognition of land cover classes going back in time. In the first phase that has been concluded, what we did was to use shallow machine learning methods. We use support vector machine for the optical data and the random forest for the SAR data. Now we have evolved this processing chain. I say a few words in a couple of slides. But the key point is then that we fuse this, and we fuse this by using a paradigm that tries to keep consistency in the products. Now, I just use one slide to share the concept, nothing more. Let us assume this is the representation of our pixel, okay, on an image for 2020, 2015, 2010. Okay. When we have Sentinel-2, we use, of course, 10-meter resolution. When we don't have Sentinel-2, we go to the scale of Landsat thematic mapper. And we are in a condition in which, of course, this means that when we have just the Landsat, one pixel represents 3 by 3 pixels in Sentinel. What we did was to create a cascade paradigm in which the final decision is taken by correlating what is happening in time from now back to 1990, so that we can take the temporal correlation in the decision process. And this helps to keep consistency, but also helps to increase the accuracy of what you are doing. Now, this is done in a theoretical, well-funded way, the cascade paradigm for classification, which is funded in the Bayesian theory, but that exploits at the end the machine learning components. Then we also represent the changes with unsupervised strategies of each pixel on a yearly basis. But I don't have really time to enter in detail. Now, just to give you the flavor of the activity, we are working on a limited area, as you have seen, but the number of tiles that we have processed in order to generate this product is already huge. Okay? We have used more than 96,000 Sentinel-2 tiles, and more than 16,000 Sentinel-1 tiles, starting from the pre-processing and so on and so forth. We have used, in terms of Landsat, more than 235,000 tiles, which is a huge amount of data, of course. And much less on the SAR side, because going back in time, it's difficult to find reliable data there. Well, so when I look at the generated products, we have generated a map with 10-meter resolution that correspond to 70,000 tiles in terms of the mosaicing that we have generated. Whereas in time series, we have generated 4,200 tiles that represent the evolution regionally of 700 tiles. So a large computational effort, but also, of course, a huge amount of data to process. This is an example of the products that we generate. What we provide are the land cover map with the best class, but we also provide the map with the second best class, so that if you like to understand the uncertainty in the decision, you have additional information. For climate modeling, this is extremely important, to model the uncertainty. And the uncertainty is also modeled because we represent as auxiliary products the posterior probability associated with the decision of the first class and the posterior probability of classes for the decision of the second. So you can understand and you can manipulate this to represent the uncertainty. We have as metadata also a product that tells you for each pixel what is the quality of the input data. We had cloud cover. When you go back in time, we have few data available. You need to know what is the uncertainty in input to the classifier. And then we have this associated with the uncertainty in output. I show you a few examples of results, just to reason a little bit on the kind of products. This is one of the maps that we have generated in Amazon. Of course, this is a very small area, at 10-meter resolution. This is the comparison with the other products that we have in CCI that is at medium resolution, 300 meters, one order of magnitude of difference. Of course, if I have low resolution, I have a more complex legend that take into account different kind of mixture. If we work at 10 meters, we can assume that more or less it's not true, but we have n members in terms of land cover classes. Then when you look at the maps, you can see that, of course, given the resolution, there are some parts that we can recognize in terms of classes, like the presence of water, that are not modeled in the medium resolution products. But more important, if you try to aggregate the percentage of the land covers that you have in this area, starting from 10-meter resolution or starting from 300, you get different results. Which means that when we move everything at the scale of climate modeling, 10 kilometers, 20 kilometers, we don't get the same kind of results. Okay, the much better modeling of the high spatial resolution then change also the perception of what is happening on the ground. Other example in Siberia, okay, again, same kind of comparison. I think you can clearly see that what you get is completely describing in a different way the landscape. Okay, this is, of course, relevant for many different applications. This map can be used in any kind of application, but also for climate. This representation is something that is different from this representation, also in terms of percentage of the classes. Other example, which is connected with Africa, okay? Medium resolution, going inside the pixel, we see something that is more structured and more complex than what can be represented with a mixed legend. Okay, I'd like to show you an example of the time series. Okay, these are just a couple of examples. This is what is happening in an area which is inside our region, in the Khartoum city in Africa since 1990. You can see in this area we have a huge evolution of the land cover. But take into account, this is the scale that we are representing, 0-20 kilometers, and the resolution of this map in reality is of 30 meters. So we have a lot of details. Other interesting example is in Amazonia. In Amazon, you know that you have this strong deforestation, okay? And when you look at this kind of products, you can realize what is the meaning of strong deforestation since 1990. Here the scale is between 0 and 60 kilometers. These are again products at 30-meter resolution, okay? You see this, but what we see in our products is that when, for example, when you look at the real resolution, you start to see that before having the deforestation, roads are constructed. So you start to see in your images that there is a new road, and then in the next acquisition you see the deforestation. So a lot of information. I would like also to show a couple of examples comparing what we have done with other products that are generated at 10-meter resolution. This is a comparison with the ESA World Cover product that is well known. This is a map, we are again in Amazonia in 2019 at 10-meter resolution we have generated. This is the map generated at the same resolution by ESA World Cover. Okay, of course there are similarities, but there are also significant differences. For example, here we don't see the river which is present in this area, which is extremely important for climate modeling, of course. Maybe less important to map if you like to generate a product at global scale, which is more general. Okay, so this means that you have products that nominally are similar, but in reality, the assumptions done for the processing are different. We try to keep the genuine resolution of the sensor, because we need that kind of information for climate application, whereas in this case there is a stronger regularization, which means that probably you don't have the 10 meters, 20 or neither 30 meter resolution. It's important to understand that there are different purposes in the generation of different maps and to select what you need on the basis of this. This is another example, same kind of comparison. We are still in Amazon. This is the land cover product of world cover. This is what we generate, okay? These are completely different representations, not only in resolution, but because we have also the seasonality of the classes and the variation of the vegetation. Of course, this is much more relevant for climate modelers as information, okay, with respect to this kind of information, which is relevant if you like to have a nice regularized map with a limited amount of noise. Of course, there are also drawbacks in this kind of approach, because if you try to go to the original resolution, you have to accept to have more errors, because of course it's intrinsic. In this case, you have more regularization. Now what we are doing is to work in the second phase of our project to increase the area that we are representing. We are trying now to generate the time series for a large part of South America and for Southeast Asia. We focus on Philippines and the neighboring area. And when we are doing this, we are also updating our processing chain. Now we use deep learning classification both for optical and SAR data. And here we use a lot of the concepts that I described in the first part of the presentation for the training, for using, let's say, old maps with the uncertainty, with the multi-instance learning for supporting the training. Okay, we are getting quite interesting results without new ground truth data in terms of production, even if I think that we need to ingest some genuine ground truth data to have a fine-tuning at the end of the model. But this is going in the direction of having a pipeline that can work worldwide at global level, which is probably the next step of what we intend to do. Now, if you're interested in the products, here you can see the link to the archive where all the products are available with the different uncertainty information. We can also navigate the products in the app that is developed by ESA in the Climate Space office. And if you are interested in following what we are doing, you can join the project. We have a large community of users, not only for climate, users interested in the products, and we inform the user when we have new products, and we are happy to have feedback in order to improve what we are doing in the future. Okay, I go to the conclusion of my presentation. I have used almost all my time. And I'd like just to recap what I mentioned in this presentation. So I think generation of high-resolution land cover products is still a challenge. We are in a condition in which we have a problem with the label data, with the quality of the label data. We are still limited use of the uncertainty information. There is a lot of activity for generating huge benchmark data set. But in many cases, this activity is done by people coming from computer vision. And all the problems that I mentioned in my presentation can be seen in many of these benchmarks. So we have to be very careful in using them, and we have to use them in a proper way, trying to understand what is the uncertainty. We have potential issue with the legend, with the inconsistency of the legend when we do this kind of activity, of merging different land cover maps, land cover products for taking the annotation of our samples. We have a problem, of course, related to the harmonization. Now, with artificial intelligence, we are in a condition in which we can improve our capability to generate products. Deep learning, foundation model, large language models, but I'm just mentioning a few methodologies. I did not enter in any detail of this. Okay? Maybe you are working in this domain, you know that there are different kinds of architecture, different approaches, a lot of promising directions. But we are in a condition in which we have still a very important limitation. The way in which we approach the solution, in many cases, is not taking into account the quantitative nature of remote sensing data. Again, this is not computer vision, but we need to ingest this as an important input in the models. There are activity in progress, of course, but this is not at the level at which this should be. We have then a problem connected with the explainability of these machine learning models. That is, we'd like to understand a little bit better what they are doing. And there are methodologies that try to describe how a deep architecture arrived to some kind of results. What are the portion of the images, the features that are more relevant, just to have a better feeling of what is happening for generating the products. And then I think a key point is the quality of the map that are generated and the different purposes for which the map are generated. We'll start to see, I think, an increase of this kind of products. With AI, you can generate your products, but the key point is to understand the quality of what you are generating. And also the assumptions. I have presented a couple of examples of products that have similar resolution, but different purpose. And of course, depending on what you are doing, you should be aware of what is behind these products in order to select the proper representation. In some cases, there is not a good representation or a better representation, but a different representation. In other cases, I think we have still the problem of the quality, the accuracy, the validation of the maps. Okay, because in CCI project, what is done by ESA, which is driving, of course, this effort, is to have an independent validation team. The group that produce the products are different from the group that validate the products. And in this way, we can have a proper validation, reliable. In many cases, in other cases, the validation is done by the same group that generate the maps. In other cases, you don't have a clear validation. And of course, this is a very important part of the story, because if you don't have a proper validation, it's difficult then to use this map for real applications. Okay, I stop here with my presentation. Thank you for your attention and for coming early this morning. I run just in background a video that we have produced with ESA that describe our projects, and of course I'm available for questions.
Thank you, Lorenzo, for the very comprehensive overview. You mentioned at the very last part the challenge of validation. Particularly, it's quite challenging validating multi-temporal products. Could you say a few additional words on that, please?
Yes, this is one of the big challenges that we have when we go back in time, indeed. Try to understand what was at that time the line cover. Of course, with the line cover, okay, we can do something that is more difficult to do when you have other kind of products that are connected, for example, with soil moisture or something like that. What we do is to start from the representation of the line cover that we have now and try to analyze, in this case for validation, this is done by the validation team in our project, and going back in time with photo interpretation to understand where we have the changes in order to have representative label samples. And this is done merging with information that comes from old map that are available. In some area we have this old map, in some area we don't have. But of course, when you go back in time, this is a challenge. It's much more difficult to have a clear validation going back in the past. Also because you start from the representation that you have now, and you start then going back to eliminate samples. So try to change the label if you look by photo interpretation to these samples. But the problem is more challenging, of course.
Thank you very much for your presentation. For me, one final reflection. I think it's very important to have always a map linked to a metadata file with the uncertainty, with the fonts, with the sources of your map, the number of training samples. So for me, we can produce a lot of cartography, but if you don't have the information of this metadata, for me, it's not a good map. It can be a very beautiful map, but it's not a very good map if you don't have the information of the quality, the accuracy, the uncertainty, and this kind of things. So for me, thank you very much for your presentation, because I completely agree with you.
Yeah, this is important, I think, and we need to push in that direction as a community, trying, to push to have this kind of products. And especially when this information is not available, it's very difficult to use the products. But this is a trend that is difficult to push, because a lot of this activity come from people from AI, okay, from computer vision. And so there is a gap, I think, between the two communities, and we need to work on that. Okay, thank you.